Okay, we're going to look at additional aspects of aqueous equilibria, meaning really buffer systems and titrations and indicators. Okay, there's such a thing called common ion effect, right? And if we look at a solution of acetic acid, we can see that we have that equilibrium that we're used to seeing at this point, with the acid and water setting up an equilibrium with the hydronium ion and the acetate ion. If we were to add more, if we were to add more acetate ion, we're going to increase the concentration of this product, and Le Chatelier's principle says that we will shift that equilibrium back to the left, or to the reactant side. Common ion effect, if we were to add that ion, okay, it's going to decrease the ionization of a weak electrolyte. It's going to decrease how much of that weak acid ionizes to the hydronium and its anion. So the formal definition of the common ion effect, the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte, and is really just simply the previous example applied to many different systems. So let's take a look at this. This is actually the sample exercise 17.1 that you may have gotten as a handout. Okay, so what is the pH of a solution made by adding 0.30 moles of acetic acid and 0.30 moles of sodium acetate to enough water to make a 1 liter solution? First thing we should do is write the equation. So I have the acetic acid in water, setting up in equilibrium with the hydronium ion and the acetate ion. You should know that sodium acetate is aqueous. Okay, the sodium, looking at sodium, sodium would react only with the negative part of water. Okay, that would potentially have an equilibrium with sodium hydroxide. Sodium hydroxide, we know, is a strong base, so there is no equilibrium, so the sodium ion is going to remain in solution. So the only thing that's going to affect our equilibrium is this acetate ion. They were nice to us and used 1 liter. If we set up an ice table, we will have 0.30 molarity. Water does not enter into the expression. The hydronium starts off as being 0, and the acetate starts off as being 0.30. Since there is no hydronium, we know that the equilibrium is going to shift to the product side. So we're going to lose acetic acid, we're going to gain some hydronium, we're going to gain some acetate ion. So at equilibrium, the concentration of the acetic acid should be 0.3 minus X, hydronium would be X, and the acetate ion would be 0.3 plus X. The Ka, if we look at the expression, is the hydronium times the acetate ion's concentration over the concentration of the acetic acid. And if we look up the value from literature, we will find it is 1.8 times 10 to the negative 5th. Because that Ka is small, we can assume that this 0.3 minus X goes to 0.30. We can assume that this 0.3 plus X goes to 0.30. plugging in the values for these, I get x times 0.30 over 0.30 is equal to the 1.8 times 10 to the negative fifth. Those cancel. X is 1.8 times 10 to the negative fifth, which is equal to the concentration of the hydronium ion. So the pH then is equal to the negative log of the concentration of the hydronium ion, which is equal to 4.74. Okay. Which is also the same value as the pKa. Oh, and checked 5% is okay. All right, so we can do a similar problem. Calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar in HF and 0.1 molar in hydrochloric. Right, so we're given some information. Ka for HF, and we're given the expression for Ka, which you should be able to do. Right, so write out the equilibrium. Remember that hydrochloric acid is a strong acid. So we have some hydronium ion present. This really ice table represents our, I'll put water over here. Remember, water doesn't enter into the equation, so we kind of ignore it. This sets up the equilibrium with the hydronium constant, or the hydronium ion and the fluoride ion. Okay, so I have HF present and I have the hydrochloric. The Cl is the anion of a strong acid, so it's just going to stay fully ionized. Looking at the change, since there is no fluoride ion, the equilibrium has to shift to the product side. I'm going to lose HF, gain hydronium, gain the fluoride ion. Again, since our Ka was 10 to the negative fourth, we can assume that the x is going to be small compared to the 0.1, small compared to the 0.2. So we have at equilibrium, we're going to assume HF is 0.2 and the concentration of hydronium 0.1, concentration of the fluoride ion, it would be x. So solving for x, 1.4 times 10 to the negative third is less than 5%. Okay, so we can find the pH is equal to 1. This all leads us into a discussion of buffers. Buffers are solutions of a weak conjugate acid-base pair, something that we just looked at. The acetic system, the HF system, all of those could be considered buffers. And what that does is it makes a solution that's resistant to pH changes, even when a strong acid or a base is added. So if we look at our HF buffer, if we add a small amount of hydroxide, it does react with the HF. It forms that fluoride ion and the and water. Okay, but the pH changes very little. Similarly, if we add an acid, the fluoride ion reacts with it to form HF and water, but it really doesn't shift the equilibrium any particular to a large degree. Okay. And we'll talk about the buffer capacity in just a little bit. All right, so general buffer calculations. We set up the equilibrium for a weak acid. You know what the Ka expression is. Rearranging slightly, we can write it like this. And this is really, we're leading up to a shortcut from the ICE table and those classic equilibrium calculations. Right? So we have this equation where you take the negative log of both sides. This is what we get. Okay. Okay. The negative log of Ka is the same thing as pKa. The negative log of the hydronium concentration is the pH. Negative log of the anion, which is the conjugate base, over the concentration of the HA, which is the acid. We get this equation. So if we're working with a buffer solution, this can be used to calculate the pH of that buffer solution. pH is equal to the pKa of the acid plus the log of the concentration of the base, which may be the anion of the acid, over the concentration of the acid. And this is known as the Henderson-Hasselbalch equation. You can still get the same answer by going through the equilibrium concentrations using, or the equilibrium calculations using ICE tables, as this equation will give you. Okay? And sometimes you have to be careful, and we'll run into a question like that as well. All right. So this is an example from it's 17.3, and we will do this in class. Actually, come into class having this done, and we'll see if your answer is correct. Oh, look, we did it. Hopefully you got 3.77. So, pH range. The pH range is the range of pH values over which a buffer system is going to work effectively. So if you want to keep a particular system within a certain pH, excuse me, you're going to have to look for an acid that has a pKa that's close to the pH that you want to keep that system at. Okay, now, be careful when strong acids or bases are added to a buffer. It's usually safe to assume that all of the strong acid or base is consumed in the reaction. So you assume that the neutralization goes to completion. This is an important thing to note. Okay? You assume the reaction, I probably should say neutralization, goes to completion. Okay, so you have your initial concentration of your acid and your base, the anion. Okay, you have a neutralization with an acid, you have a neutralization adding a strong base. Recalculate what you have in the solution. Recalculate what you have after that neutralization occurs. Then you're going to use your equilibrium calculations to calculate what the new pH will be. Okay. So again, determine how the neutralization of the reaction affects the amounts of the weak acid and its conjugate base in solution. So you have to know what's being left over in that solution to set up the correct equilibrium, if there is one. Okay, if you still have that weak acid and its anion, then you can use the Henderson-Hasselbalch equation to determine the new pH of the solution. This is where I'm going to put a little asterisk. You need to watch that the capacity of the buffer is not exceeded. if you end up after neutralization that you don't have any anion or any of the weak acid left, you may have exceeded the capacity of the buffer, and your pH of the solution is going to be the excess hydronium ion you have, or it's going to be due to any hydroxide that you have in excess. So looking at a quick example, we have a buffer made by adding 0.3 moles. This is the same problem that we had before, although now we're going to add 0.2 moles of sodium hydroxide, right? Before the reaction, okay, before I add that hydroxide, we knew that the pH was 4.74 from a previous example. But now I'm going to add that 0.02 moles of sodium hydroxide. This is the stoichiometry. I have 0.3 moles of the acid, 0.3 moles of the anion, and 0.02 moles of the sodium hydroxide. After the reaction occurs, all of my hydroxide is gone. It reacted with the acetic acid, so this lost 0.02 moles, and this gained the anion. I gained 0.02 moles of the anion because this is the neutralization reaction that we assume goes to completion. Notice the one-way arrow. These are the starting points then for our equilibrium concentration. Calculations, I keep saying that. So for the new Henderson Hasselbalch, we use, remember, the concentration of the base up top, which is the anion, and this is the concentration of the acid. And this should be 28.280. I'm hoping the math works out then. Okay. That ends our discussion on buffers. Next up will be titrations.